Okay, time to get started. Before we get into the math, a couple of quick announcements. So first of all, I commented on the first day of class that attendance does count as part of the grade. You might have noticed I have not been checking attendance, right? And that's because drop add period, students add, students drop. It's confused, in and out. And it's just more trouble than it's worth to figure out, who's excused and who's not excused, and it's just not worth dealing with. However, of course, as y'all know, drop add ends tonight, or at least the wait list portion of drop add ends tonight at 11:59. So with that in mind, hopefully our class roster will be fixed as of tonight. Given that, we are going to start checking attendance. Friday will be the first day. Today's Wednesday. Yeah, so Friday will be the first day. So attendance is going to be checked. It is part of your course grade. Not much, but a little bit. Y'all got an email from me last week at some point talking about the grading system for the course. So there's a course-wide grading system, well, anyway, there's in the whole document, and, letter grades on exams and fixed percentages and all this. So there's a clarification email that I'm going to send out today at some point, talking about that remaining 10%, the instructor portion 10%, et cetera. So anyway, email from me coming soon about that 10%. Attendance begins to be checked, counts as part of your grades starting on Friday. Okay. All right, so back into math. We talked about this last time. 2x2 determinant is defined by this little formula. Weird little formula that I think y'all all saw in high school. Okay. 3x3 matrix determinant is defined by this weirder looking formula. By the way, it turns out both of these formulas are special cases of a general formula for n by n matrices. It's a little bit harder to write down that formula. There's games you can play to talk about how to compute it, but in terms of writing it down as a crisp formula, it's a little bit more effort. And it's not what Math 212 is about, so we're going to stop here with 3x3. If you take Math 216, you'll see much more about determinants. Okay, so y'all have probably seen some applications of determinants, but it's usually in high schools it's presented as, well, it tells you the following about a system of equations, or something like that, but it's usually pretty vague and it's not justified. Well, we're not going to justify everything we're going to say about determinant either. It's actually surprisingly deep stuff to deal with really, properly. But I am going to tell you some non-algebraic facts about determinant. Here's the first one. This is about the 2x2 determinant. So this totally could have been presented in a high school class. They usually don't. Right, so this is probably new to most of y'all. So, neat fact, if you were to have a couple of vectors, an ordered list of vectors, two vectors in R2, and make two things out of this ordered list of vectors. On the one hand, make those two vectors by, with their components, the rows of a matrix. On the other hand, take those two vectors, draw them geometrically, and make a corresponding parallelogram. Like so. The determinant of the matrix tells you a lot of information, geometric information about that parallelogram and how those vectors look geometrically, as follows. So if you know the determinant, whether it's positive, negative, or zero, tells you about the ordering. That tells you whether this is, as I've drawn it here, a counterclockwise ordering, or depending on if the picture were different, right? It might be clockwise, or it might be neither. Right? So the determinant tells you about the geometric nature of the listing. And here's why that's weird. Here's why that's an eyebrow raiser. Determinants defined algebraically. This wacky little formula right here. Right? Totally algebraic. There's nothing in that definition that says anything about, well, see, look at the A and the B and the C and the D and interpret geometrically. No, it's a formula, right? And yet that formula picks out something unavoidably geometric about how you wrote down those vectors. That's really pretty remarkable. Yeah. Okay. Here's the other thing that it tells you. The determinant, by way of its how big it is, tells you the area of that parallelogram. Well, again, that's another sort of like, where did this geometry come from, right? This formula, AD minus BC, is very algebraic. What this theorem is telling us it relates to is, area is extremely geometric. It's an eyebrow raiser. Okay. All right. So, really surprising fact about this innocent little looking, 2x2 determinant formula. And again, they didn't show me this in high school, and maybe you might have seen it. Just out of curiosity, how many people saw this fact in high school? A few. Okay. Hey, very cool. All right. Most of you probably did. Notice that you can simplify all three of these cases into saying that the area is always the absolute value of the determinant. Right? And you can arguably, sort of rewrite these correspondences as the sign tells you the order. Positive means counterclockwise, negative means clockwise. 0 means neither. Okay. All right. Quick example. Here's a pair of vectors. Now notice this is not just two vectors. This is an ordered list of two vectors where this one is first. Right? That's the first one listed. And then this one here is second. Right? So putting them in that order, making a matrix out of them. That one's first, make it the first row. This one's second, make it the second row. Right? Likewise, with the when you make a picture out of them, this one's first. Right? That's listed first. This one here is second. And you can immediately see the correspondence between the sign and the order. So let's see here. So compute that determinant, AD minus BC. It's negative. And that negative is indicative of this being clockwise. Right? From the first vector to the second vector is a clockwise rotation. Everybody on board? Okay. Likewise, the 5 represents that this area is 5. Now, I think that's also pretty surprising. What's the sort of the blunt brute force? What's the high school geometry way to compute this area? The high school geometry approach would be to say, okay, well, we're going to have to compute. Let's see. The formula for a parallelogram is I need to know that length and I need to know that altitude, right? Where that's a right angle. And both of those are going to require square roots. Computing this length, I'm going to be looking at the Pythagorean rule on that vector. There's square roots involved. Right? How would I compute that altitude? Well, let's see. We can use dot products to compute that distance. And I can use square roots to compute that distance, because that's the magnitude of a vector. And then the Pythagorean formula would tell me that distance. So square roots all over the place, and I could compute the length of the base and compute that altitude and formula. And this little calculation here with the determinant, no square roots, 4-function arithmetic, 3-function arithmetic. It's a little mysterious that it could be that easy. Anyway, I like to dwell on that. I think that's fun. Okay. So, turns out there is a very analogous fact about vectors in R3, or said differently, about 3x3 determinants. So, this theorem, as I have it written here, you'll notice it's written on the page very analogously, and this is on purpose. There's a strong analogy between this theorem and the one previous. So if you have, let's see if I can remember the colors we used. Yeah, I forgot. Okay, no problem. We'll just use different colors. Here's 3 vectors, A, B, C, out of which you can make a matrix. Make sure to respect the order, right? Whatever order they're written down, that's the order that you list them as rows. You can also make a parallelogram out of them. And as you would sort of expect, the determinant of the matrix, the determinant of that matrix tells you a lot of stuff geometrically about this picture. So the sign of the determinant tells you about the handedness of this listing. And again, don't forget the ordering. So this is A is first, B is second, C is third. Right? So the handedness, whether that listing of these three vectors is right-hand order or left-hand order, is given to you by the sign of the determinant. Right? So sign tells you the handedness. And the size of the determinant, the absolute value of the determinant, tells you about the size of the parallelogram. Namely the volume. Totally analogous to the previous theorem. Okay. All right. Now, just out of curiosity, how many people saw this in high school? Fewer. Okay. All right. No problem. Anyway, neat fact. By the way, this continues. You can define determinant for 4x4 matrices. Some of y'all might have seen, in fact, how to do that. And you can use that to construct a notion of order on quartets of vectors in R4, whatever that means, right? And a notion of, something kind of analogous to handedness. It's hard to put a label on that because it's in R4 and we don't know how to visualize that, right? But there is an algebraically analogous notion that comes out of determinant and a four-dimensional notion of volume. I mean, it's not volume, right? Volume's three-dimensional notion. Right? And in the same way that volume is an area, area is a two-dimensional notion. So there's some four-dimensional kind of next step in that process, again, that you can get your hands on with determinants. That's kind of wild. Okay. Again, quick example. Here is a listing of vectors, three vectors. Make a matrix. Again, the order that they are listed is the order that you make them the rows of that matrix. Can make a let's see, what is that? A parallelepiped, right? They call it. It's like a parallelogram, but with three vectors. And the positivity is telling you about the fact that this is a right-hand order. And right-hand order, right? I can just do a visual aid with my hand, but it's hard to draw a right hand on the page. Okay. And the volume of this thing, man, that'd be a tough thing to compute. Imagine, go back to high school tools and think about how, it's the area of the base times the altitude. That altitude, though, wow. I mean, how are we going to compute that altitude? We would need to know how this vector projects down here perpendicularly. And how do you compute that distance? I mean, that's starting to seem like a pretty tough problem. Right? Very difficult geometry problem from a high school point of view, but that volume easily computed with determinant. Works out to be an integer. No trig, no square roots, nothing nasty. All right. Okay, so with all this discussion, we spent a bunch of time talking about handedness, right-hand order, left-hand order, clockwise, counterclockwise, all that business. We talked about determinant. We've seen some surprising geometric features of determinant. And now we have the tools that we need to finally talk about kind of what we came here for in the first place, which is cross product. Remember, we talked about dot products as our first vector products. And now here's the other kind of product. Again, I'm going to start with a formula. I'm just going to write it down. There it is. That's our definition of cross product. For vectors in R3, by the way. Only vectors in R3. There's some analogies that break down with dot product. Dot product is, remember, it was this weird fact that dot product of two vectors is not a vector. Dot product of two vectors is a number. Right? Well, the cross product of two vectors in R3 is a vector in R3, as you can see with this formula. So this is arguably more sort of an expected kind of a construction in that sense. Okay. The other thing is, the formula we wrote down for dot products in R3, there's an analogous formula for dot products in R2. It's exactly what you would think. Just multiply and add the coordinates, right? It has all the same features. And ditto in Rn. Dot product works just fine, no problem at all. Right? Cross product does not. Cross product is defined only for vectors in R3 specifically. There is no cross product in R2. Doesn't make any sense. Right? So be real careful about that. Make sure not to write down, so errors of type are, not things to avoid if at all possible. Don't make errors of type. Don't try to do operations with things that you can't do that operation with. Real bad sign, right? So don't try to cross two vectors in R2, or don't write cross product of two vectors in R4. Okay. All right. Okay. Here's some algebraic properties of the cross product. Again, we tend to kind of roll our eyes and yawn a little bit when we see the algebraic properties, but we shouldn't, because these are brand new operations, and hey, you never know, and now we see why you got to worry about that kind of thing. The cross product, it's a product in a way, and it's in certain senses, but it's not commutative. Easily checked. Right, just write down the formula for W cross V, follow the formula above, but put the W's before the V's, and you don't get the same thing. You get the exact negative. All right, so you've got to be careful going forward on this, right? So y'all have developed a lot of habits in having, y'all been doing algebra now for several years, right? Since, golly, maybe even more than that, 5-6 years possibly of, doing algebra. And you've gotten really sort of accustomed to, you can just kind of shuffle things around in a product. CAB, well, that's ABC, and you can just kind of move things around. Like, that's how multiplication works. No, it isn't. Not with cross product. Right? So, heads up. Be really careful. You got to resist these urges, these sort of strong temptations to shuffle letters around in products, because to put them in whatever order seems aesthetically most convenient, or something like that. Right? You can't do that with cross products. You got to worry about that minus sign. Okay. Here's another one. This, I'm not sure what to call this. It's vaguely reminiscent of an associativity, right? But it's really not. So for example, we are not saying that U dot V cross W is equal to, let me put a question mark here, right? Don't copy this down. I'm about to write down some garbage, right? I'm not saying that this is equal to U dot V cross W. We are not saying that at all. In fact, this is another error of type. This doesn't make any sense at all. Let's look at what we have here. Right? A couple of different things that are bad with this. For one thing, that is a scalar. You can't cross a scalar and a vector. That's not a thing, right? Look at the formula. The formula requires two vectors, right? So the right-hand side doesn't make any sense at all. Right, so what you might say would be, what you would expect associativity to look like. That's not what this is saying. It's a little bit different from that. By the way, and then you might also say, okay, well, let's just change this to just a scalar multiplication. Then that's a scalar, that's a vector. I can't cross multiply them, but I can scalar vector multiply them. Maybe that would be true, but no, it's not. And here's how we know this. Scalar times vector, this thing here is a vector. Right? Whereas this thing here over on the other side is a dot product of two vectors, which is a scalar. Right? So this is another error of type. There's no way this could possibly be true they're not even the same kind of critters. How could they be equal? Right? Is everybody on board? Okay. All right. So this is a weird property that we're claiming here. Again, vaguely sort of smacks of associativity, but it's not. Okay. All right. By the way, here's another thing to notice about this property. You might have noticed that there's only 3 items that we're claiming are equal here, but there's 6 different ways to order 3 vectors. How come I'm only writing these 3? Did I get kind of tired? Is there an implicit ... here? Answer, no. It's only these 3 that are equal. And then the other 3 are equal to each other, but are not equal to these. And the difference between them is comes out of the fact that you have this minus sign here. So, for example, U dot W cross V is the exact negative of this. Right? So this construction, by the way, this construction where we dot a cross like that, it's called a triple product. Triple products turn out to have some really interesting features. We're going to talk about that as we go along today. The triple product construction takes the 6 different orderings of these 3 vectors and breaks them into 2 sets equal within each of these sets, but that are negatives of each other. Okay. All right. Okay. Lastly, if a cross product is equal to 0, then there's this geometric consequence that the vectors are parallel, or one of them is the 0 vector. That one's not particularly reminiscent of any algebraic properties we've seen before. You can prove this algebraically, but there's kind of a more satisfying way to see this by way of a geometric argument that we're going to talk about in a few minutes. So let me sort of delay on all of these. By the way, both of these also easily checked with algebra. You could just crank them out, directly confirm, which is good for rigor, but it leaves you feeling unsatisfied. Like, okay, well, I guess it's true, but it doesn't. But why should it be true, right? So one thing I'm always trying to encourage students to do is, one thing, you have to know what is true, but it's also good to try to understand, try to get a feel for why it should be true. Not even necessarily why it is true, but why should it be true, right? And so you can prove that this is true, but why should this be true? Where's the intuitive satisfaction? That's not going to come from algebra. We'll talk about that in a few minutes. Okay. All right. Here's one. By the way, this one is one that I think you should absolutely crank out the algebra on. It's not hard algebra. It's very fundamental to the cross product. Everyone should do this once in their lives. And it's a really important feature of the cross product. The cross product of 2 vectors is always orthogonal to both of the input vectors. V cross W is always orthogonal to V, and V cross W is always orthogonal to W, both. And this situation comes up fairly regularly where you have a couple of vectors and you need to find a third vector that's orthogonal to both of them. The cross product is exactly the thing that does that. It's a very handy tool. We're going to use this a lot in the next section of the book on lines and planes. So neat fact. Now, how do you confirm this? Well, orthogonality, keep in mind, is defined in terms of dot products, right? Do you want to confirm that V, for example, you want to confirm that V is orthogonal to V cross W? Well, compute that dot product. Confirm that dot product is 0. Dot product equals 0 is the definition of orthogonal. Right? So you've got a formula for V cross W, you've got a formula for the dot product, crank it out. Again, everyone should do this once in their lives. I already did mine. Right? So crank it out. It's not that bad. There's only 6 terms. It turns out that they cancel, and there's your 0, and there's your orthogonality. Yeah?
So the third vector formed by the cross product, does it form a right-hand order when we get the...
we'll get to that later. It's a great question, and we don't quite have what we need to answer that question yet, but it's an excellent question, and we are going to answer that. Yeah. Okay, so compute that dot product, confirm that they're both 0. That gives you the orthogonality. Okay. Okay, now here's the next thing I'm going to do. By the way, let me remind you, there's a lot of different ways to go through these ideas, a lot of different ways to prove the various formulas that we're in the process of deriving. I go through this the way that I find the most satisfying. The book does it a little bit differently. Other books do it differently than that. Other instructors are going to do it differently. This is just my sort of preferred way to do this. But I like to make the following observation. Let's go back to the formula for cross product. Here it is. Notice that these coordinates individually all look like little 2x2 determinants, right? They had the same structure, da minus da, right? So let's just write it like that. There we go. Coordinates all listed as 2x2 determinants. Now these are coordinates because these are the coefficients in front of the standard basis vectors. Don't forget we talked about that last week at some point, that a vector with coordinates can be viewed as a linear combination of the standard basis vectors where your coordinates become the coefficients. So I'm using that trick here, which ends up being important here. Okay. All right, and then you say, wait a second, now this didn't work out quite right. Look at this one here. That one is not a determinant. That's a negative of a determinant. Okay, it is. That's right. I could, by the way, have written this as a determinant, but I would have had to write then these rows in the other order. I would have had to put the W's on top of the V's, or arguably I could have switched the columns, and it would have worked out. I could have made that a positive determinant. I want to leave it, though, as a negative of a different determinant. Seems weird. Momentarily we'll see why. Here it is. Why did I want to leave that as a negative of a determinant? Because now I notice that this formula structurally looks just like a 3x3 determinant, kind of, with an big asterisk that we have to worry about. But if you were to just take what's written down here and take the determinant per the formula a couple pages back, and okay, it's E1 times, and you cross out the row and the column, and you look at the submatrix, you get that term. Right? And the next one is, you take the E2 and you cross out the row and the column, and there's your E2. We have that weird minus sign in the formula for determinant. How handy. There's that minus sign that I left there on purpose, right? Seemingly awkwardly, 30 seconds ago. Okay, etc. So, it's kind of strange, but if you just write down, based on the symbolic definition of determinant, this determinant, you get exactly this formula, namely you get exactly the cross product. So that's a very weird fact, but a cross product is what I call a symbolic determinant. It's very, very convenient. By the way, I urge y'all to memorize this formula. In my life, I have never memorized this formula for cross product. It's the most crisp, right? But I just know myself that if I were to try to memorize that formula, I would find myself during an exam being like, "Oh gosh, is it V1W2 minus V2W1, or is it V2W1 minus, oh gosh, which way does it go?" I just wouldn't remember. I don't have the ability to keep that straight, and you might not either. This, though, very easy to memorize. Put your standard basis vectors across the top. Put the first vector in the next row. Put the second vector in the last row. Everything's in order. There's no mysterious, switches of the numbers, and everything just keeps track for you. So this is what I memorized long ago, and I never looked back, and I did not memorize the other formula. I encourage you also not to memorize the other formula. I encourage you to memorize this one. Okay, now a confession, I do have to note that this is a little bit of an abuse, this notion of determinant. We define determinant for a matrix. A matrix is supposed to have in it elements. Those elements are supposed to be real numbers. What's going on here? That's not a real number. That's a vector. Can you do that? Is that legal? Well, that's not the point. The point is, if you take a symbolic point of view on determinant, ignore what these things are. Ignore that that's not the right kind of thing there. You're not really supposed to do that. Then this formula works great in that way. Okay. All right. Okay, last observation then, and this super important one. What would happen if I took a dot product of V cross W that we've been discussing, right, with some other vector U? Well, here's the formula for how to write down a dot product. You take one of the vectors that you're dotting, you write down its coordinates. Oh, look at this. I have those coordinates explicitly written out already. You take the other vector that you are explicitly dotting, right, and you multiply one coordinate at a time. Okay, so, well, let's see here. So I want to use what I've written here. I need to put a U1 there, and a U2 there, and a U3 there. Right, so this dot product is, there you go. I just multiplied, the blue coordinates times the green coordinates, and that is what that dot product would be. And then I make the observation, okay, well, structurally, then that looks just like the formula that I just trampled. It's just that I put U's instead of E's. So, likewise, if I just put U's instead of E's here, I get a way to rewrite that formula for that dot product. So, that dot product, this, multiplying it out, this thing that I have circled in purple, in reinterpreting as a determinant, is that determinant. Yes?
Why can't you just put the U's in place of the E's? Why is it not E times U? Why is it not both of them? I'm just doing that for kind of sort of structural convenience. So really, I'm multiplying the blue coordinates that I have underlined here times the green coordinates that are U1, U2, U3. Right? There is no E1, E2, E3 in here anymore. I've trampled those. Those are now U1, U2, U3, and that's what that dot product is. And then, having trampled in that way, then I say, hey, look at that. The formula that I just wrote down with the U's looks just like what that had been previously. I just replaced the E's with the U's. So it's more just kind of a notational observation. So V cross W is just like the determinant thing, not with the E's?
The V cross W has as its coordinates, remember, right here. V cross W has as its coordinates these three determinant factors. Yeah, that's right. Okay, so there's some algebra to slowly and carefully look at and persuade yourself that okay, well, I guess that all kind of works out. But the punchline, very important, is that this dot product can be computed with a determinant. Now, let me say that a little bit differently. This triple product is computed with a determinant, and that's an enormous result that we're going to make massive use of in this section and elsewhere in the course. Triple products are determinants. And by the way, couldn't be more convenient in terms of how the things lay out. First vector, first row. Second vector, having written it in this way, second row. Third vector, third row. Real straightforward. Okay. All right. So here's one of the beautiful things about this formula. I already understand the determinant geometrically. We have these neat facts about volumes and right-hand order and all that business. We already understand dot products pretty well geometrically. So we have a formula here that involves several operations, most of which we understand. And this is what's going to allow us to gain further understanding of the cross product. By way of this formula, we're going to learn about the cross product by using what we already know about the dot product and determinant. Okay. All right. Okay. Couple neat facts then.
this fact that we talked about a few minutes ago, the cross product is always orthogonal to the two input vectors. Hey, we already proved that. Well, y'all, I already assigned y'all to prove that on your own. You write down a certain dot product and just crank it out. It's not that much. And just observe that dot product algebraically easily seen to be 0. So we've already proved that this is true, right? What I'm coming back to here is the question of, okay, well, yeah, but why should it be true? Where is the geometric satisfaction that, of course, you don't get from algebra, right? So why should this product be orthogonal, cross product be orthogonal like that? Okay, well, we know orthogonality comes down to dot product being 0. If I want to decide, if I want to know why those are orthogonal, then those are what I have to dot. Oh, hey, check it out. That is a triple product. On the previous page, we showed that triple products are determinants. Oh, wait a minute. Determinants give you volume. Oh, wait a second. These vectors, as listed, 2 of them are the same vector. So I have V, V, and W. And if you make a parallelepiped by taking 3 vectors, 2 of which are the same vector, you get a flat parallelepiped, right? This is a cardboard box ready for recycling. Right, smushed down. So this volume here, clearly 0. The volume is clearly 0. Therefore, that determinant is 0. Therefore, the triple product is 0. Therefore, that dot product is 0. And therefore, those vectors are orthogonal as desired. Right? So what I like about this is there is no sort of like crank it out, collect terms, algebraic sort of mystery. These are all kind of geometrically relatable ideas. And I find that very satisfying. So anyway, I hope you'll find that satisfying too. It's also a very clever way to make use of these various properties that we've talked about of cross products and determinants and triple products, etc. Okay. So here's another neat application. One of the algebraic properties we wrote down was this thing. Why is this true? And again, you can crank it out algebraically. Where's the satisfaction in that? Right? How does cranking it out algebraically address the question of why should this be true? And I argue as follows. These 3 things individually, they're all determinants. Well, they're all triple products. You can see that right there. Triple products are all determinants. Determinants represent volumes of parallelepipeds. So what we're really looking at here, this algebraically expressed statement, we're looking at 3 volumes, kind of. You got to worry about pluses and minuses. Right? 3 parallelepipeds, and in all 3 cases, the parallelepiped involve the vectors u, v, and w, right? Possibly written down in a different order, but the order that you write down u, v, and w doesn't change the fact that the resulting parallelogram is the parallelogram defined by u, v, and w. It's the same parallelogram for all 3 of these expressions. Same parallelogram, same volume. Does that make sense? Now we do have to worry about the minus signs, right? Well, remember minus signs come down to the order and whether the order is right-handed or left-handed. Well, we know from earlier discussion on Monday that when you cycle, so what we've done here is you take the vector at the end and you move it over to the beginning like that. When you cycle, you don't change the handedness. Right? So these 2 things, they're in a cycled order in relation to each other. Therefore, they have the same handedness, and therefore these 2 determinants have the same sign. And likewise, this going over there, these 2 things have the same sign as well. So, therefore, these values are all equal, and that's why, again, all geometric. That was a totally geometric argument that gives you some, again, hopefully some intuitive satisfaction of not just that these are true, but why these are true, why these should be true. Okay. All right. Here's a neat fact. The book proves this in a very different way than I do. You're very welcome to look at the book's proof. It's fine. No problem. Perfectly valid. I like mine better. No surprise. Here's what I like about mine. No trig. Right? The book's proof uses trig here. So let me show you how to prove this without any trig. By the way, so here, first of all, what is this statement saying? This is saying if you look at a cross product of two vectors, the magnitude of that cross product is equal to the area of the parallelogram defined by those vectors. And a quick reference. This notation here, I don't think that notation is used in the book. I may have made this up on my own, or maybe I saw it somewhere many years ago. I don't remember. But I think this is a very convenient notation. Two parallel lines followed by two vectors indicates that this is the parallelogram defined by those two vectors. Very convenient. So I'll be using that a lot. Okay, so the assertion here is that the magnitude of the cross product is the area of the parallelogram. Again, you can make a trig argument, see the book. I'm going to do what I like to call a mathematical bank shot. This is this is an approach to math that is surprisingly useful. Okay, that you're here and you want to get there, and we're going to get from here to there by going that way. Right? And somehow by going that way we'll end up over there, thus the metaphor. Okay, so I'm going to compute this thing, right? Which, big question mark. Why would I compute that thing? I'm trying to see why these two things are equal. This is neither of those. So who cares what this is? And believe it or not, again, growing off in a totally different direction, this is going to give us what we want. So here's the argument. So first of all, notice that this is a triple product. First vector, second vector, third vector, right? Determinants are triple products. Yeah? Everybody see that? Okay, determinants are triple products. Oh, having written that down, we notice that this particular triple product happens to be a dot product of a vector with itself, and therefore magnitude squared. So that's one calculation here, which is, by the way, not what we're interested in. We're interested in two completely different things. So it's not clear what we've gained by showing that that's equal to that. Let's set that aside for the moment. Now I'm going to compute that same thing, though, in a different way. So forget about this guy. Let's compute this now. It's a determinant. Determinants are volumes. Right? Are vectors. Like that. So I'm interested in this volume. Yeah? Okay. How am I going to compute that volume? Well, that volume... special. Good news. We already know these are right angles. So this is not just a random parallelepiped. This is what you might call a partially right parallelepiped. Right. So there's this base down here. Let's see here. Let me make some color choices. We've got this base down here, and then we've got a height. And the volume, I remind you of high school geometry, the volume is going to be the base times the height. The altitude, if you will. Okay. Well, because it's a right angle, that altitude is just the length of this cross product. Right? And then times the area of that base. Yeah? Everybody good? Okay, great. We have successfully computed something we're not interested in twice. What's the point to what a silly exercise, seemingly in uselessness. We computed this and got that. We computed this and got this. Who cares? Oh, Well, we care because we just computed the same thing two different ways. Therefore, these two things are equal to each other. Oh, yeah. Cancel a common factor of magnitude V cross W, and we got our result. So that being that is what we wanted to show in the first place. Total bank shot, right? Again, we started off thinking about something we're not interested in. The result that we wanted fell in our lap. You'd be surprised how often this comes up in math. Everybody on board? Okay. All right. So again, no trig. The book's argument on this, angles and trig, and the more sophisticated the tools are that you use in your calculation, the less sort of intuitive satisfaction there is. I think so. I think this is much more satisfying as to, kind of why this sort of should be true. This is a great proof to chew on. But don't think about this just step by step, but think about, what was the motivation and why, how might you have come up with this on your own? By the way, I do not expect that you could have or would have come up with this on your own. Somebody showed me this argument, right? I didn't dream this up on my own, I don't think. Certainly you're not expected to have dreamed this up on your own, but you can think to yourself, okay, Monday morning quarterbacking, how could one reverse engineer and think that, come to think of it, this determinant, we're interested in an area, this is a volume. Hey, areas and volumes they're pretty closely related by simple geometry formulas. Hey, maybe this is an interesting object to consider. Anyway, you can kind of piece your way through and make sense out of it. So try to digest this argument. I think it's a really good one. Okay, so next fact real quick. Again, one of the properties that we listed with no justification other than, check the algebra. Right? Was this one? Yeah, question.
Quick question about the proof. So the final step, you have to divide both sides by magnitude.
Yeah.
So
Yeah.
could that be
0?
zero?
Yes, it could, and we're about to address that. Yeah. So this right here, if the cross product is 0, then that means that either the two vectors are parallel or one of them is 0. And how do we see this is true again? So this was presented as a, you can algebraically write this down, and that gives you some algebraic properties that you can play with algebraically and conclude this conclusion. So easy way to see this. This fact immediately gives us that, right? If the magnitude of the cross product is equal to the area, well, cross product being 0 would certainly mean the magnitude is equal to 0, which by the above formula means the area is equal to 0, and vice versa. So this fact here gives us that connection, and this connection here is pretty immediate. And it's just, think about games with vectors and areas, right? If you have a parallelogram whose area is 0, right, here's two vectors, here's the resulting parallelogram. How are you going to make that parallelogram have area equal to 0? You're going to need to make those vectors parallel, or you're going to need to make one of the vectors itself the 0 vector. Otherwise, there's your parallelogram, the area is not 0. Right. So that purple connection is, I think, geometrically satisfying. The green connection follows from what we just proved, and therefore we have this connection. Okay, neat fact. Okay, little bit more to do. Somebody asked a question, how do you know whether the cross product is, which of the two possible ways when there's two different directions that are perpendicular to V and W. Right, given two vectors V and W, does it go the one way or does it go the other way? How do you tell? And how would we even how would we make the distinction in the first place? So that it is something we have to worry about. By the way, do notice that knowing these two vectors, we know that parallelogram, and that dictates the magnitude of the cross product. right? So the directions of V and W tell you a lot about the direction of the cross product. The parallelogram defined by V and W tells you about the magnitude of the cross product. We have almost a completely geometric characterization of the cross product. Forget algebra. We know its magnitude in relation to an area. We know its direction in related to other directions. It's all geometric talk. And it all comes down to this last question, though, of, well, but which is it? Is it that one or is it that one? And the answer comes from on the previous one of the previous very recent arguments. This determinant, we argued, was a magnitude squared. That was right here. Right, determinant's a triple product's a magnitude squared in that case. And here's the thing, that's clearly never negative. And that means that this is never negative. That means it's a right-hand order unless you have some anomalous case where one of the vectors is 0 or two vectors are parallel or something weird like that, those anomalous cases are always easy to identify. If one of the vectors is 0, that's easy. So other than the anomalous cases, always right-hand order. That's always a right-hand order, and cycling allows you to conclude a more sort of useful version of that, and that is that this is always a right-hand order. So when you are taking a cross product of two vectors v and w, you can use what we call the right-hand rule, which is, again, using your right hand, first finger in the direction of v, second finger in the direction of w, no hand yoga, your thumb points in the direction of the cross product. Everybody on board? That tells you which of these it is. Okay. Let's see. It looks like I'm out of time, so we'll call it a day right there. We'll pick up here next time. I'm going to go through this last page of this section pretty quick because we're not as where I'd like to be on the schedule. So I'm going to start picking up the pace a little bit. But anyway, see you all on Friday. Yes, question.
When will you assign the
thank you. Thanks for the reminder. So every week I owe y'all an email on Wednesdays after class. Realistically, it tends to be Wednesday afternoons. In that email, I will tell you which sections of the book we've finished talking about, and therefore which sections will be due that Friday. So I owe y'all an email today, and those questions as listed on the syllabus, corresponding to the sections that I identify, will be due start of class on Friday. By the way, this is one of my rules, start of class on Friday. So I don't want students working on the homework in class. It's just, that's completely unproductive, right? So very start of class right here on Friday. Okay, see y'all later.
It's graded for accuracy.
Yeah, it's mostly. I mean, we can't grade the whole thing, so we'll grade 5 out of the however many questions, and they're graded for validity of your argument. It's not just whether the number's right? So they're graded for the quality of the work. Let's say that. Yeah. Yep. Okay, see y'all later.